You see? So this is very, very thing, like kind of reasoning that I go through. So a lot of times in the book you might see, they just throw out the definition. They say just buy it. C is Q over V, and then here's how capacitors add up. And then you're left wondering, why do they add up different than resistors? I don't get it, you know. Well, it's just because in order to satisfy our very understanding of what a good capacitor is, it must be Q over V. And then you can say opposite. What's the definition of a low capacitor? Something that's a poor capacitor. Well, it's something that even if I put 1,000 volts on it, I still get a low charge. It doesn't store a lot of charge. So high V, low Q. You see? Whereas here, high V, low Q would give you a very high capacitance. So it doesn't make sense at all. Throw it out, okay? How about this now? R is V over I. What if I had tried to make life easy and I defined R is I over V, and then resistors would add just like capacitors add. So can I do this? Well, go through the same reasoning. What's the definition of a good resistor or high resistance? Okay? It's something where even if you put a lot of voltage, the current is low. Oh, it resists the flow of electrons. It's a good insulator, right? So high resistance got to be something where the V is high, I is low. Okay, V is high, I is low, you get a high resistance. Okay? V is high, I is low, you get a small resistance. No, that doesn't make sense. You see? Boom, there you go. This is perfect. This is the kind of thing that you guys should be asking yourself. Why is something defined something the way it is? And then try to go through the reasoning. And later when we go to chapter 32, we're going to define what an inductor is. The inductance of an inductor. And we're going to see this definition. EMF induced in a coil divided by the rate of change of current in the coil. Or it could be defined this way. The rate of change of current in a coil divided by the EMF induced in the coil. So when we get to that chapter, I'll go through the same reasoning. I'll show you why this one doesn't make sense. Again, you see? So that's perfect. So now you see why capacitor is the way it is and why it's opposite to the resistor. Okay, so now how about power? How does power add up in series or parallel? All right? Well, the same can be said about the power as about energy. Remember with capacitors, the energy stored in each capacitor just simply adds like a scalar. Doesn't matter if they're in series or parallel. Well, same thing can be said about power. The P total of the battery is equal to P1 plus P2 plus P3 plus Pn of each resistor. Okay? For the resistor, you can use what formula can you use for the resistor to find the power? Well, we did it on Monday, right? VI or I squared R or V squared over R, depending on which one you know, which of them is the easiest. Or this is the P for the resistors, P sub R. How about P for the battery? The power that the battery is producing, okay? Well, it's the current going through the battery times the voltage across the battery. For that one, you can't use I squared R because the battery is not a resistor. So the only one you could use is VI. Okay? Okay, let's now do a circuit